Light is fundamental. It illuminates our world. It allows us to see the cosmos. Understanding light is key to unlocking the secrets of the universe. We experience light in two ways: ray optics and wave optics. Ray optics treats light as straight lines. This helps us understand how lenses and mirrors work. Wave optics reveals light's true nature. Light is actually made up of electromagnetic waves. Light travels incredibly fast. It races through space at approximately 300,000 kilometers per second. This speed is constant and represents the ultimate speed limit in the universe. Understanding light's properties is essential. It allows us to develop technologies like telescopes, cameras, and lasers. These tools help us explore the vastness of space and the intricacies of the microscopic world. Ray optics simplifies our understanding of light. It assumes light travels in straight lines called rays. This model helps explain how shadows form and how light interacts with objects. Reflection is a key concept in ray optics. When light bounces off a surface, it is reflected. Mirrors utilize reflection to create images. We use mirrors every day. Refraction occurs when light bends. This happens when light passes from one medium to another, like from air to water. Refraction is why objects appear distorted underwater. Lenses utilize refraction. They can focus or spread light rays. Lenses are crucial for eyeglasses, telescopes, and microscopes. These instruments extend our vision. They allow us to see the very small and the very far away. Mirrors are everywhere. We use them daily. Mirrors reflect light rays, creating images. There are different types of mirrors, each with unique properties. Plane mirrors are flat. They create virtual images that appear behind the mirror. These images are the same size as the object and are reversed left to right. Spherical mirrors are curved. They can be either concave or convex. Concave mirrors converge light rays while convex mirrors diverge them. Concave mirrors can create real or virtual images. Real images form in front of the mirror. Virtual images appear behind it. Convex mirrors always produce virtual, upright, and diminished images. Telescopes use mirrors to gather light from distant objects. These mirrors are often very large to collect as much light as possible. This allows us to see faint objects in the night sky. Refraction is the bending of light. It happens when light passes from one medium to another. This bending occurs because light travels at different speeds in different mediums. The refractive index is a measure of how much a medium bends light. A higher refractive index indicates that light travels slower in that medium. Total internal reflection is a fascinating phenomenon. It occurs when light passes from a medium of higher refractive index to one of lower refractive index at a steep angle. The light is completely reflected back into the denser medium. This principle is used in fiber optic cables. These cables transmit light signals over long distances with minimal loss. Fiber optics revolutionized communication, enabling high-speed internet and data transfer. Section 5. Light's true nature: waves of energy. Light is more than just rays, it also behaves as a wave. Understanding light's wave nature is crucial for explaining phenomena like interference, diffraction, and polarization. Light waves are electromagnetic waves. They consist of oscillating electric and magnetic fields. These fields are perpendicular to each other and to the direction of wave propagation. Interference occurs when two or more waves interact. This interaction can either reinforce the waves, known as constructive interference, or cancel them out, which we call destructive interference. Diffraction is the bending of waves around obstacles. It explains why we can hear sound around corners and why light spreads out after passing through a narrow slit. Polarization refers to the orientation of light waves' oscillations. Sunlight is unpolarized, meaning its electric field vibrates in all directions. Polarized sunglasses reduce glare by blocking light with certain orientations. Section 6. The quantum leap: light as particles. In the early 20th century, our understanding of light underwent a revolution. Scientists discovered that light can also behave as particles called photons. This dual nature of light, exhibiting both wave-like and particle-like behavior, is known as wave-particle duality. It's a fundamental concept in quantum mechanics. The photoelectric effect provided evidence for light's particle nature. This effect occurs when light shines on a metal surface, causing electrons to be emitted. The energy of these emitted electrons depends on the frequency of the light, not its intensity. This observation could not be explained by classical physics. Albert Einstein explained the photoelectric effect by proposing that light consists of discrete packets of energy called photons. This groundbreaking work earned him the Nobel Prize in Physics in 1921. Section 7. Inside the atom Bohr's model and the quantum world. The discovery of light's dual nature revolutionized our understanding of the atom. In 1913, Niels Bohr proposed a model of the atom that incorporated quantum theory. Bohr's model depicted the atom as a small, positively charged nucleus surrounded by electrons orbiting in specific energy levels. These energy levels were quantized, meaning that electrons could only exist at discrete energy values. Electrons could jump between energy levels by absorbing or emitting photons of specific energies. This explained the discrete spectral lines observed in the light emitted by excited atoms. Bohr's model was a significant step towards understanding the quantum world. It paved the way for the development of quantum mechanics, a more complete theory of the atom and its behavior. Section 8. The Heart of Matter, Nuclear Physics. Nuclear physics explores the atom's nucleus, which consists of protons and neutrons bound together by the strong nuclear force. This force is the strongest force in the universe, overcoming the electrostatic repulsion between the positively charged protons. One of the most important concepts in nuclear physics is mass-energy equivalence. This principle, expressed by Einstein's famous equation E equals mach squared, states that mass and energy are interchangeable. Nuclear reactions such as those occurring in the sun involve the conversion of mass into energy. This process releases enormous amounts of energy. Nuclear fission, the splitting of an atom's nucleus, is used in nuclear power plants. Nuclear fusion, the combining of atomic nuclei, powers the sun and other stars. Understanding nuclear physics is crucial for developing technologies like nuclear power and medicine. It also helps us understand the processes that occur in stars and the early universe. Section 9. The future is bright. Semiconductors and beyond. Semiconductors are materials with electrical conductivity between that of a conductor like copper and an insulator like glass. Their unique properties have revolutionized electronics and technology. Silicon is the most commonly used semiconductor. By adding impurities or doping it, we can control its electrical properties. This allows us to create transistors, the building blocks of modern electronics. Transistors can amplify or switch electronic signals. They are essential components in computers, smartphones, and countless other devices. p-n junction diodes, formed by joining a p-type semiconductor with positive charge carriers and an n-type semiconductor with negative charge carriers, are fundamental electronic devices. They allow current to flow in one direction only, making them essential for rectifying alternating current to direct current. Logic gates, built using transistors, are the basic units of digital circuits. They perform logical operations on binary inputs, enabling the complex computations that power our digital world. Understanding light and its applications has led to remarkable advancements in technology and science. From the telescopes that peer into the depths of space, to the lasers used in telecommunications and medicine, our exploration of light continues to illuminate our understanding of the universe and our place within it.